What we're going to do in this section is use sample data to make claims about the population. So here we're getting into inferential statistics. What does a sample tell us about the population? Specifically in this section, we're going to talk about if we have some sample proportion, what does that tell us about our population proportion? And starting with just being given a sample proportion, what we'll sometimes call this value is the point estimate. In that this value that we get from our sample, in terms of what we know for our data, this is our best estimate for P, for our population proportion. So if we don't know anything about our population proportion, our best estimate that we can go with is the sample value. Some things that come into play is that we should have random samples, it should come from large sample sizes. So with this, we'll end up checking some conditions to kind of make sure that we can trust that sample proportion. But if we pass those conditions, those values should be pretty close together. But instead of saying that our sample proportion is just equal to our population proportion, what we want to end up doing is create a range of values. What we're going to do is create an interval, and that's why it's called a confidence interval, is we're going to find some lower bound value and some upper bound value. And what we're going to say is between those two numbers should be P. We don't know where it is, but it should be somewhere in that interval that we find. So the idea being, if we have a distribution of samples, say we have a sampling distribution of proportions, and our population proportion's right in the middle there. When we take a random sample and collect p hat, we should be landing in the middle here. There's a high probability of getting a sample that's in the middle, and with that, what we can do is wherever p hat lands, say we're landing a little bit to the left here, so we have this sample proportion, it's fairly close to our population proportion. What we want to do is create a range of values. So we make this lower bound and upper bound, and what we do is we use this margin of error to say how far above should we go and how far below should we go. But if we do this to a random sample and create this interval around it, what should happen is that population value should land within that interval. Now there can be the weird cases, and this is where we'll never be very 100% certain of our interval. But there are cases where we take a random sample and say we land way outside in the tail there. And we create this interval, but we don't capture that population proportion. When we work through this section, we're going to have this level of confidence attached to our confidence intervals. So if we say we're 95% confident in it, simultaneously we're kind of saying 5% chance that we're wrong. And it'd be this 5% chance that we're landing in these weird regions out in the tails that just aren't very likely for taking a random sample from the population. So we'll be confident in our intervals, but there is this error that can come through as well. So what we want to do is understand the sampling distribution and then create this margin of error to get this lower bound and upper bound. To help make our margin of error, we're going to use something called standard error. And this formula is very similar to what we used for sampling distributions. For sampling distributions, we use the square root PQ over N. But as we work through this section, we're not going to know our population values. Everything we work on is going to be based on sample data. So we won't know anything about the population. So with that, our formula changes a little bit. And where it changes is just in the numerator here. So that where we had population values, now we're using sample values. So where this was standard deviation for our sampling distributions, now we call it standard error since it's based on sample data. So standard error is this formula right here, and it gives us an idea of our curve. And that if we have some curve with some center to it, moving by basically standard deviations would be the same as moving by standard errors in this case. So In this though, I keep drawing this normal curve, and to know that we have a normal curve, we have to pass our conditions. So with these, we're going to be checking our conditions, which will be very similar to our sampling distribution of proportions. We need to have independence. We need to have randomization. And we need to have a large enough sample size. So we need to check that success-failure condition. Now here, there's the slightest change in notation when we used it for our sampling distribution of proportions. Again, we had that population data. We knew what P and Q were. But now, all we have is sample data. So we're going to use P hat as our best estimate for P. So what we do is take N times P hat, N times Q hat, and both of those should be more than or equal to 10. So the only difference in notation here from what we did in sampling distributions is that these are now sample values, not population values. So let's see how this confidence interval is formed. Say we have a survey of 2,500 HR professionals and showed that 1,200 use social networking sites to research job applicants. Let's state our sample proportion. So our sample proportion is this proportion of HR professionals that use social networking sites to research job applicants, which is the 1,200 out of the 2,500, which will be a 0.48. And in this, we'll usually need Q hat as well, which again, to find Q hat, it's just the opposite of P hat. So we take 1 minus 0.48, which is a 0.52. So here's our sample information, and then our standard error. We would take the square root of 0.48 times 0.52 out of our sample size of 2,500. And rounding that to 4 decimal places, there's going to be, you'll get this decimal out of 0.009992, essentially. Rounding that to 4 decimals, though, it's going to round up to just a 0.01. So that would be our standard error. So, draw how the sampling distribution model for P hat would look. And what we have to do here is work with the assumption that our population proportion, which is usually the center of our sampling distribution model, we're assuming that is about equal to the sample proportion that we found from this set. Now, to work with that assumption and to work with the bell-shaped curve, we should check our conditions first. So, independence, that would come through since how they research job applicants should be independent of each other between different HR professionals. Randomization, they didn't state that it's a random sample, but we'll go ahead and assume they took a nice random sample of those 2,500 HR professionals. And then the success-failure condition, taking our sample size times 0.48 and our sample size times 0.52, and that'll be 1,200, this will be 1,300, and both of those are more than or equal to 10, so we're good there. So since we pass our conditions, this sampling distribution is bell-shaped. So we know we have this curve here. Now, for the center of the curve, we're going to have 0.48. Typically, we would put our population proportion there, but we don't know what it is, so instead we use this point estimate. Our best estimate's at 0.48. Then, if we want to get an idea of the number line, for moving standard deviations, instead of using standard deviations, we have to work with the standard error, because again, with sample data, that's the best that we have. So if we add 0.01, we'll have a 0.49, 0.5, 0.47, 0.46. So you can get an idea of the types of sample proportions we should be getting out. if this 0.48 is close to our population proportion. So what we're showing here, it's a distribution of sample proportions using sample sizes of 2,500. That sample size is coming through from that standard error. If we change our sample size, then this whole number line will change because the standard errors would change. So distribution of p-hat using sample sizes of 2,500, and what we're doing is we're assuming that our population proportion is close to 0.48 when making that distribution. So with this, what we can do is start thinking about where do we expect 95% of sample proportions to fall. And what we're going to do here is start with the empirical rule that we learned about. And we're just going to use this as kind of a quick guide for forming our confidence interval, but we're just going to use it here and then never use it again. We're going to use GeoGebra to get better values out. So example here with empirical rule, but in general with future confidence intervals, don't use it. So our 95% rule from our empirical rule said 95% of the data is within 2 standard deviations. So what we could do is with our distribution up above here, we go 2 standard deviations below, 2 standard deviations above, that gets about 95% of the data. So 95% of samples should land between those 2 numbers. So our population proportion is likely to be in there. If we take a random sample and this proportion should be close to 0.48 in the population, then if 95% of all samples land between those 2 values, our population proportion would have a high probability of landing within there too. So this 95% coming through, and it's this kind of 95% chance of landing in there, but mostly it leads to a level of confidence that we have. What we could say here is that we are 95% confident that our population proportion, rather the proportion of all HR professionals, so now we're talking about our population instead of just sample, of all HR professionals that use social networking sites to research job applicants, is between, and we get this range of values coming through. We get this lower bound of 46% and upper bound of 50%. It's between 46% and 50%. So some things that come through in this wording here, we have this level of confidence, and it's coming through the fact that to build this interval, to get to that lower bound, to get to that upper bound, we use these 2 standard deviations away. Like the calculations for these numbers, I got that 46%. I could have found that by taking 0.48 and subtracting 2 of our standard errors, which was 0.01. And this 50% came from taking our 0.48 and adding 2 standard errors. And it's by using that number 2 there as our multiplier with the standard errors that's helping us move 2 standard deviations above, 2 standard deviations below, which links to our 95% in the empirical rule. So that's where the level of confidence comes from. It comes from the distance that we go above and below. So the fact that starting at 0.48, we went 2 above, 2 below. If I went 1 above, 1 below, if I just used 1 standard error above, 1 standard error below, then we'd be talking about 68% confidence. Or if I went 3 standard errors above and below, then I could be talking about 99.7% confidence coming from the other values in the empirical rule. So that's where our confidence comes from. In the wording, we should have this kind of long wording. What that comes down to is describing our population proportion. When we get to our conclusions with these, it's all about estimating what's happening in the population. So our samples are just going to be a starting point, but then from there, we're making big claims about the population. So within our wording, we shouldn't be talking about our sample at all. We just use our sample to get an idea of how these two numbers come out for our actual confidence interval. So these calculations that we did, this form here is what we use for calculating confidence intervals. We start with that point in the middle, which is going to be our sample proportion. And then we always want to move up and down by the same distance. And then for this, using the empirical rule, we use 2 each time, and we multiplied that with the standard error. And what this would do is give us about 95% confidence. But what we want to be careful of is that our sample proportion is good, that's calculated from data. Standard error is good, that comes from data. It's this value of 2 that's making this a rounded value, where we would have to say, even above, I made a mistake, we are 95% confident. I really should have said we are about 95% confident, because the empirical rule is just estimations. They're not exact values. But we have technology that can help us out and make exact values. So that's our next example here. What 2 proportions would capture exactly 95% of the values? So what we could do is improve on this value of 2. Instead of moving just 2 standard deviations above and 2 standard deviations below, what would be the accurate number to move above and below that would get 95% of values in between? Notice that this description of moving 2 standard deviations away from the mean, that relates to a z-score. Z-scores are all about how many standard deviations away from the mean are we. So what I'm going to do is to figure out this value that's going to improve that z-score so that we have exactly 95% of values. I'm going to go to our standard normal curve. And it's on that curve where I'd have a center of 0. I have my standard deviations, or rather my z-scores. And from there, I want to find the cutoff values to the point where I get exactly 0.95 in the middle. It should be close to 2. Again, 2 is just a rounded value for what we do here. What we want to know is, what is this actual z-score that puts 95% of values in the middle? Now, as we've talked about before, in GeoGebra, we can't set just a middle percentage. So what we're going to need to do is think about what's happening in the tails too. So this cutoff point, such that there's 95% in the middle, that would leave 5% overall in the 2 tails. And then we just want to divide that up into 2. So this z-score that we're looking at, while it does make 95% in the middle, to actually find the value, we need to think about having this 2.5% above that value. So let's go to GeoGebra. For our standard normal curve, we want to create an area to the right, and we want this area to the right to be 0.025. And that number right there, the 1.96, that's the z-score that we want to get. As you can see, it's really close to 2, but if we actually create an interval going from negative 1.96 up to positive 1.96, that gives us exactly 95% between those values. Whereas if we used negative 2 to positive 2, it's close to 95%, but it's too much. It spreads too far. So if we use 2 for our intervals, the intervals are actually too wide. But if we use 1.96 as this multiplier, that's going to give us exactly 95%. So what we want to use is this 1.96. So where we had this formula up above of using our sample proportion plus or minus that z-score times our standard error, if we're looking for exactly 95% of the values, we would want to use 1.96. Instead of moving 2 standard errors above and below, we actually just want to move 1.96 standard errors above and below. And that'll give us exactly 95% of values. So what we're going to do is take our 0.48 plus or minus 1.96 times that standard error of 0.01. For simplifying these, it's a good idea to completely simplify the right-hand side first. So we would take that 1.96 times a 0.01, and then from there, separate into the subtraction and addition. So you're going to have 2 calculations, one where you subtract and one where you add. So the subtraction would give us our lower bound, which would be a 0.4604. And then the upper bound would be where we add. Sorry, I wrote that as multiplication. So 0.48 plus 0.0196, which would give us a 0.4996. And this is a more accurate interval. You can see it's very close to what we found above, 46% to 50%, but this is better. And then with our conclusion, we could say exactly 95%, and then we would say 46.04% to 49.96%. And this would be a better interval to use. So as we move forward with these confidence intervals, and 95% confidence is one that comes up fairly often, don't use 2. That was just for an example. We want to use this 1.96. If you want 95% confidence, this z-score you want to use should be 1.96. And this z-score is a special one that we'll be calling z-star. And that value doesn't change. If I gave you a completely different example and said use 95% confidence, you want to use that z-star value. So this is how we calculate our confidence intervals, how we end up with a lower bound and upper bound. First thing we have to do is check our conditions, but once we check our conditions, we can go through this calculation. So our calculation separates as we have our sample proportion on one side of the equation, or rather the expression, plus or minus, then you're going to have this special z-score. And when it was 95% confidence, it was 1.96. But this z-star value, which is also called a critical z-score, can change. And it's going to come from looking at our standard normal curve, since it's a z-score. It's going to be a standard normal curve such that we center our percent confidence. And in the next video, we'll talk about how to find all these different types of z-star values and some key ones to memorize. And then the third piece is our standard error. So be careful, there's standard error and margin of error. Standard error is just this calculation of the square root p hat q hat over n. Margin of error, it has the multiplication with z-star included. So if they give you margin of error, you don't need to multiply by z-star. If they don't give you margin of error and just standard error, then you need to find that z-star value. So just be careful with those 2 different wordings there. So that's our introduction to confidence intervals, and the next videos will kind of break down finding the z-star values, getting our wording correct for our conclusions, because those are very important, and then just practice calculating values.